Hey there, everybody. So today we're going to talk about volumes of solids, and the way we do that is we take a function, something like f of x equals the square root of x, and we want to draw that graph, which I've already drawn. What we need to find out first, and I'll show you guys this in class, is basically we need to find out what the area is going to be and where are you going from and to. That you're going to rotate the solid. Usually it's around the x-axis, but it can be really around the y-axis or even a line. So we're just going to use the simplest version of this. And let's say we'll go to, just to make it easy, we'll go to a revolution from 0 to 9. So we should know now how to figure out the area under this curve, between this curve and the x-axis. So I know how to get that area. So what we want to do in order to get the volume of the solid is we're going to take this area and we're going to rotate it around the x-axis. So if you can imagine, it's popping out of your video screen, rotating around, going back underneath and through the video screen on the back part of the video screen, and then looping back around. So I'm going to show you another video of some very good 3D pictures of this. So the thing that we want to try and understand is if I take a sliver of this, if I cut this revolution, or if I cut the solid, what kind of slice am I going to get? Okay, so if I was to take this and to stand it up on its head, what I'm going to get is sort of a bullet shape, where this is going to be. And again, 3D is a little bit tough to draw, but basically you get, okay, so that is this solid rotated around or this area rotated around the x-axis, and it gives you a solid which looks something like this if you stand it up. So again, just to get a visual reference, the x-axis is going to go through the bullet like that. So that's kind of what it looks like. So we want to know what that volume looks like. So as I said, if I cut this, what kind of shape am I going to get? Well, hopefully you can see that if I cut through this solid, I'm going to get a circle. So if I know what the area of one of those circles is, then I can find the volume, believe it or not. So what I want to do is I want to take a radius perpendicular to perpendicular to the axis of rotation, which is right here. And what is one of those radii of the circle going to look like? My area formula for one of those circles is going to be pi r squared. What's one of my radii going to look like? Well, the radius goes from here on the axis to here on the function. So I know the height of that function. It's going to be the square root of x. So one of the radii is going to be the square root of x. And subsequently, really all of the radii are going to be the square root of x, because that just gives you the height up until 9. So what am I going to do here? Well, to set this up, I'm going to integrate from 0 to 9. And I don't just want to integrate one piece of the area. I want to integrate all of these slices. So I'm going to go from 0 to 9, and all of those slices are going to be pi r squared dx to get the area. And all I'm going to do is substitute that square root of x into r. I'm going to substitute square root of x in for r squared, so the indices stay the way they are. That pi, since it's a constant, can go outside, and the replacement substitution is going to be the square root of x squared dx. So you can do the algebra right in the integral, and so that comes out to be pi. Oops. That comes out to be pi on the outside of the integral from 0 to 9 of x dx. Well, that's a pretty easy definite integral to integrate, because x, the antiderivative of it, is going to give you x squared over 2. And I'm going to be multiplying that by pi, the constant that's just brought down here. And I'm going to be evaluating that from 0 to 9. Well, if I plug 9 in there, I'm going to get 81 pi halves. And I'm going to be subtracting 0 pi halves, which obviously is just going to be 0. So the volume of that whole thing is going to be 81 pi halves. So the video that I have for you here gives you a better visual of what the 3D looks like. So this is actually a girl in an AP Calculus class came up with, and this is her solids of revolution. She had some pretty slick software to do this with. So what you're doing here, or what she's showing you here, is the x, y, and then the z axes, just to give you that three-dimensional look. So this is a Riemann sum. So this is back to what we originally did when we were doing when we started trying to find areas on the curves. So the first thing you need to do is find the area, and then you're evolving that around the x-axis, and you're going to create this 3D looking thing, almost like a phonograph, the old-timey phonograph speakers. So she's gonna talk about a disk and a washer method. We just do disk methods, because really it covers all of the possibilities that you could have. But that's what it looks like. So now there's two functions. So you're trying to bracket the area in between first, and she's revolving this one around the y-axis. Which again gives you one of those phonographs, but this one, the other one was solid, and this one has some area in between it. It has some volume missing from it. So she's going to do what's called the washer method. But we always are going to do the disk method. Okay, so hopefully that gives you some idea about area of curves revolved around either axes, the x or the y axis.